Narrated lecture slides on atomic theory. So today we will be covering sections 7.4 through 7.6. Again, we're breaking up chapter 7 just because it's a lot of material, and we wanted to kind of make it a little more manageable for you to watch the videos. So now that we've talked about kind of issues that were had with the classical way of thinking of light, and things like that, and how we now understand that light has wave-particle duality, and how materials and matter have wave-particle duality, we're going to start talking about the model of the atom, and we're going to start with the Bohr model. So in your 152 days, you had the plum pudding model and all sorts of other crazy stuff, the Rutherford gold foil experiment. So we're going to start talking about the Bohr model, and we'll be ending with the quantum model. Please understand that we kind of use the Bohr model even after we talk about quantum because it's nice and easy to draw. We just understand that when we draw it that way and we're referring to things, that we know that's not really what it looks like now. That we understand there's this level of quantum to it that we're going to kind of keep in the back of our heads. So again, right around the same time that we started talking about the photoelectric effect and the issues that we were seeing with our classical understanding of light as a wave, there were other scientists out there that started talking more about these quantum states, right? These specific energy levels. For energy of electrons and quanta and photons. And so this started getting people thinking about things like, well, what does the atom look like? Because we know there are electrons around a nucleus and things like that. So Bohr was the one who came up with the idea of kind of the planet model, we call it, where like you would pretend that the nucleus was the sun and that the electrons were the planets that were fixed in a path, orbiting around the nucleus. And it was a really good base. It's not correct, but it worked for hydrogen and other one-electron systems, and we'll talk about why in a little bit. But we now know it's not correct, but it was a really good first shot at things. So again, as we start talking about this material, you should be comfortable with the difference between a ground state and an excited state. We're first going to talk about ground state, and then we can talk about excited state. So in the quantum model, unlike the Bohr model where we have this planetary fixed rotation of our planets, or excuse me, of our electrons, we're going to do in a quantum model, the electron in the hydrogen atom moves around the nucleus and is in a circular orbit. So instead of it being a flat disk, it's going to be more of a sphere. Okay, the tendency to revolve around electrons flying off the atom is by the attraction of the charge, right? So again, this concept is still very similar to Bohr's in the fact that we know that the nucleus is positively charged and the electron is negatively charged. So the reason the electron isn't flying off into space at any given time is, is because of the attraction between the positive and negative charges. Now, what's going on when we talk about how electrons absorb light and then they kick off and all that kind of stuff? Remember everything we talked about in the photoelectric effect? What's going on here? Remember that our electrons are found in those discrete energy levels, right? They don't exist on the ramp. They exist somewhere on the stairs. And so when an atom is hit by energy in the form of light and it absorbs it, it's going to take in energy, and that will allow it to transition to a higher energy state. If that higher energy state is relaxed, it will emit light and other energy in other ways, but light is one of them, and that will bring it to a different transition state, a lower energy state. So if an atom takes in photons or takes in energy, it's absorption. If an atom gives off photons, it's emission. Um, and these within an atom, we're talking specifically about the electrons within the atom here. So when we're talking about absorption and emission, please keep in mind that these are jumps in energy levels, and that we know that the energy levels are discrete. It's not any energy level. It has to be a specific energy level. Go from energy level 1 to 4, or 1 to 5, or 1 to 3. Those are, it can do all of those jumps, but they all have different energies associated with them. And we can't go to like energy level 2.5. That doesn't exist. So again, we can tie in what we talked about with the emission spectra and the absorption spectra. Absorption spectra is going to be when the electron takes in energy, right? And all the energy, again, if we're looking at the visible light spectrum, and we're looking at a spectra for that, would look something like this. These are the ones it's absorbing. When it that would get it higher in energy. When it wants to relax, it's going to emit energy. And when it emits energy, it's going to release that energy in the form of light. And when it does that, those have specific wavelengths associated with them. We know from the first video that the wavelength and the frequency of a light, or a photon of light, has an energy associated with it. And so the energy between these two levels, this high state and this low state, is equivalent to the amount of energy that is released. The energy difference between the ground state and the excited state is equivalent to the energy absorbed. So a couple different ways we draw this to represent it would be something that looks like this. This would be an energy level diagram for electronic transitions. And so here this blue line is showing us emitting, going from an excited state of n equals 5 to a relaxed state of n equals 2, n equals 4 to n equals 2, n equals 3 to n equals 2. All right. Here's that same concept again, but now we're doing it kind of how we get the line spectra, right? So we said, okay, if I'm going from n equals 5 to n equals 2, there is an energy associated with that, and this is a bigger energy than this. Would you agree that the red arrow is smaller than the blue arrow? That means that the blue arrow has more energy, change in energy, than the red arrow. We know that if something has higher energy, the frequency should be higher as well, which means the wavelength is smaller. Something with a less energy will have a bigger wavelength and a shorter frequency. And this is how we get those colors, because we know that in the visible light spectrum, we know that our blues are going to have a higher frequency than our reds, and green's kind of in the middle there, and this is how we end up with those line spectrums. Okay, so this new model for the atom, right? Bohr was the first one to kind of describe the electron energy levels as discrete or quantized. Only certain levels are allowed, right? We're back to that concept of the stairs. Also, we know now that, right, electrons move between these levels. To do so, they either emit light or absorb it. They can do other things too. So they don't only emit or absorb light within the visible light spectrum. They can lose energy in the form of heat. They can lose energy in the form of vibration. There's a lot of different ways they can gain or lose energy, but the one that we're focusing on, because it's a very visual one and easy to represent, is light, obviously. Since the electron energy states are quantized, right, the light emitted from an excited atom must be quantized and appear as spectral lines. So this is how we get those line spectra, where they're very specific. Bohr showed that for single electron systems like hydrogen gas, a helium cation, or a lithium 2 plus cation, the orbit energies can be given by the following equation. So here's the energy, negative Planck's constant times the speed of light, and then we have the Rydberg constant here as well. Now, because all of these are constants, you don't need to memorize all of them. H3RH equals this. It's one number. That's all the whole number you got to memorize, because you don't need to memorize all these because it's the same thing. They're all constants. So when you have this equation, it's a little less daunting if you start writing it and realizing that that's what's going on there. And then we can talk about this 1 over n squared thing. This n is the whole number. This is that principal quantum number. This is that energy level, n equals 1, n equals 2, n equals 3. So we can associate an electron and say, okay, an electron that is in the n equals 2 orbital is going to have so much energy associated with it. And then maybe we want to know how much energy it would require to get to the n equals 5 orbital. So we could calculate what energy would be in the n equals 5 orbital, and we could subtract that from the n equals 2 orbital. So all orbit energies have negative values to them. And again, this is in terms of us kind of giving direction, okay? The value negative or positive is telling us more about the direction of the energy flow into the system or out of the system than actual quantitative value to it. So in the n equals 1 orbit, right, the ground state, the lowest energy, right, would be the ones closest to the nucleus. Then you have n equals 2, 3, 4, 5, so on and so forth. Hypothetically, there are infinite numbers of energy levels for every atom. But realistically, you know, when we look at the periodic table of elements and we talk about orbitals like SPDF, after 7, we're not associated with the nucleus anymore. That there's so much space between that electron and the nucleus of that atom that electron really isn't hanging out with that atom anymore. So we just call it infinity. Which is nice because when we do math with infinity, it usually comes to 0. So 1 over infinity squared is going to be 0, and it makes math very, very easy. So when we want to figure out the orbit energies, if we're trying to figure out how much energy is associated with an absorption or the emission of some light from an electron, we can solve for that by the change in energy. So when we do this, we always take the final energy level and subtract it from the initial. So sometimes if it's being absorbed, the final would be higher than the the final would be higher than the initial. And if it's emitting it, the initial will be, or the final will be lower than the initial. So when we do that, if we're absorbing, right, we're going to have a positive change in energy. If we're emitting, we're going to have a negative change in energy. So again, the positive or negative just tells us directionality. It's just telling us, are we emitting or are we absorbing this energy? So again, right, we have this concept of energy of a photon is h nu, and we can go through and start utilizing that to calculate these different energies required. So again, this is a nice question for you to go ahead and try and solve on your own first. I would encourage you to do that and then look at the answer that is in the worked out questions or the worked out calculations in the end of the module and the resources. So I'm asking you to calculate the energy required to excite a hydrogen electron from the n equals 1 level to the n equals 2 level. And I've given you a little reminder of the equation up here. Remember, these are all constants right here. These guys right here are all constants. So it makes it really easy that we don't have to remember what that number is. So once you've done that, go and check and make sure that you have gotten the correct answer. So the Bohr model was a really good first shot at trying to understand how an atom is built. There are things that were correct and there were things that were wrong. So it's the first time we start thinking about this idea of quantized energy levels in an atom. It also is the first time that we're starting to see concepts of this circular motion. Now, remember, Bohr thought it was like a planet rotating around or orbiting the sun, so like a disk. In quantum, we understand that it's more like a sphere, so it's a 3D space. So there's still circular motion going on, but it's not 100% correct. As the electrons become more tightly bound, right, as they become closer to the nucleus, right, the energy is more negative relative to the zero energy of the reference state. So wherever it was, as it moves closer towards the nucleus, we're going to have more negative. If it moved more away, it would be more positive. As the electron is brought closer to the nucleus, the energy is released from the system. So there are obviously some issues with Bohr's model as well, right? Mathematically, this prediction only works, or mathematically, this only works at predicting one electron systems. It doesn't work for a 2-electron or a 3-electron system. The electrons are not in orbit, right? We figured that out later. That's what we said, right? A disk versus a sphere. In order to develop a model that worked for all the atoms, including the electron energy levels, the scientists modeled the matter after a wave. But we know now that the electron can also behave like a particle, and that's where we started having problems. That this wave-like classical understanding of the electron, or excuse me, the particle understanding of electron wasn't going to work. We had to also look at it as a wave. And this is what led to quantum and wave mechanics. And down here, I've just kind of written it fully out for you. This is how you would go about figuring out the change in energy between two energy levels. So I've written it fully out for you here. All right, so the last problem for you in the worked out section of the materials that you can go and look at after you've solved it are these questions here. Calculate the energy required to completely remove an electron from a hydrogen atom in its ground state. If we're completely removing the electron, that means it's going to that n equals infinity energy level. And then lastly, calculate the maximum wavelength of light capable of removing the electron from these states. So you first have to figure out the energy level, and then once you figure out the energy associated with that level going from n equals 1 to n equals infinity, or n equals 2 to n equals infinity, you're going to have an energy. And if you have an energy, we know that we can associate that with a frequency. If we have a frequency, we know we can associate that with a wavelength. Okay, so moving on from here, we're going to start talking about quantum mechanics a little bit. We are not going to go into so much depth as I had mentioned earlier in quantum mechanics. It's beyond the scope of the course. We would need to require you to have a much higher math than we want to have at a Gen Chem level. So as we said before, we're going to come to a lot of the same conclusions that we came to in 152, but we're going to be looking at them from a quantum perspective. Things like matter, right? Our electrons have wave-like properties to them. That's that wave-particle duality. We can't give exact locations of electrons like we could if it was in orbit. We can only give probable locations, and we'll explain why. We can model these probabilities mathematically and graph them, and when we do that, we get shapes. And that's where those weird shapes come from for the SPD and F orbitals. These probability graphs are called orbitals. And one important aspect of these things is that we need to understand that this represents only about 95% of the possibility. There's always about 5% chance that it could be somewhere other than where we predict it could be. So the Schrödinger equation. This is where I wanted to bring up the fact that we are not solving these equations. You do not need to worry about solving these equations. You need to go take differential calculus, and then we can solve these equations. So this is just to show you where, if you decide to continue in your chemistry career, where you will go if you take physical chemistry. So let's start talking about these probability spheres, these probability orbitals. So we call this a probability density distribution, and we call it chi-squared. So that's what this little symbol here is, for electrons in the 1s orbital, okay, or any s orbital for that matter. And what ends up happening is it kind of looks something like this. And it looks like a circle, but in fact it's actually a sphere, right? This is the XYZ plane, so it's 3D space. The closer to the center, the greater the density is, and more likely the electron will be there. But there's still a chance, even down here, that we're going to see the electron. Now remember, like we said, this shape, this sphere, represents only 95% of the likelihood of finding it there. That's a fairly good percentage. But there is a 5% chance that it will be somewhere outside of this sphere. And doing the math would give us this physical shape, and that's how we come up with the fact that the s orbitals are spherical in shape, is because the math tells us that's the probability density of where it would be. So all s orbitals are spherical, okay? As we go from n equals 1 to n equals 2 to n equals 3, so on and so forth, the s orbitals get bigger and bigger and bigger. And what ends up happening is we end up with these nodes, and that's what you're seeing here. So it's like layers, okay? We know that if it's gonna be in the s equals 1 or the s equals 2, it can't be in between. It's not like there's an s 1.5. So this node is this space where it cannot exist. It's either in the 1 or the 2 or the 3 or the 4, right? That's where these kind of nodes, these spaces of non-probability are. Another way you could think about this probability density is think of like a fruit-bearing tree. Most of the fruit will probably fall pretty close to the tree. And then as you get further and further away, there might be the occasional few pieces of fruit that hang out pretty far away from the tree. But it's all still that space where the apples could be. But we know that the bulk of them will be towards the center. And that's what we're seeing here, right? This is that distribution, the same way we're showing it here in terms of the math determining it. This is just kind of to give the same example of it. All right, so that's the s orbitals. The p orbitals, people describe them kind of looking like bow ties. Some people call them dumbbells. But again, what we're dealing with here is something that is shape depending on the math. This is the probability sphere for a p orbital. It's not this or this, it's the whole thing together, okay? It's very important to understand that it's not, well, it's over here or over here. It's in this whole space. That's what the probability is telling us, somewhere in here. Now, there are 3 degenerate energy levels of p orbitals: the px, the py, and the pz. And as you can imagine, they lie against the x, y, and z plane. So if we lump them all together, right, they would sit right on top of each other, okay? When we say degenerate, what we mean is that the pz is no greater in energy than the px or the py. They're all the same energy. So we're not going to have one fill up before the other. For the purposes of our class, you don't need to differentiate between px, py, and pz. Obviously, as we go from the 2 to the 3 to the 4, so on and so forth, the p orbitals would get bigger as well. And there is a node in the p orbital. Right here in the center is a node. So when we talk about the probability of finding the electron in the pz, let's just say I'm talking about the pz orbital right here, it's over here or over here. There's a node here, so it doesn't exist here. But it's this whole thing. It's not this side or this side. It's the whole thing. D and F orbitals, we start getting some pretty crazy shape. For the most part, D orbitals look like clovers, and then we have this little guy here. And then our F orbitals get even more fantastic looking. And again, this is all based off of those probabilities of where we're going to find those electrons. The last concept we're going to talk about in this section, in this video, are quantum numbers. So each electron in an atom is unique, and we can give it basically like a mailing address. So that's essentially what quantum numbers are. They're like the mailing address to call out to describe a specific electron in an atom. And there are a couple different portions to their address, just like there are for when you send a letter, right? You have to put someone's name, you have to put their street, you have to put their street number, their city, their state, their zip code, right? If I wanted to find John in California, well, there are a lot of Johns in California, but if I wanted to find John Smith in San Diego, California, all right, I'm getting there. If I gave a zip code, that would probably be even better. If I gave a street, that would be even better. And then if I gave the address, the number of the house, that would be really great. So that's what we're doing here, is basically calling out specific things about each element or each electron so that we can talk about a specific electron. And there are 4 different quantum numbers that we give to make a full address. There's the principal quantum number, the second quantum number, also called the angular momentum, the magnetic number, and the spin. And they're represented by different symbols. N is the principal number, and this is what we've been talking about since like 152 days. This would be n equals 1, n equals 2, n equals 3. What level are we in? Then there's the L, the M sub L, and the M sub S. And we'll talk about each of these. But basically, L will determine the shape. So is it an S, a P, a D, or an F? The magnetic number, the M sub L, will give its orientation. And so if example would be if we had a P, if we were a p orbital, this would tell us whether we had the px, the py, or the pz. And then the spin, remember, think back to your electronic configurations. We know that in each subshell that we can fit 2 electrons, right? So we know that we can have them go in opposite directions. So one is going up, one is going down, or we refer to them as plus 1/2 or minus 1/2, just the directionality of the spin. For the purposes of our class, I'm not going to call out whether you need to know that it's the plus 1/2 or the minus 1/2, just that it's one or the other. So, the principal quantum number is something you're already familiar with. This would be n equals 1, 2, 3, so on and so forth. These are all whole numbers, and they increase in size as we increase the number. So we know that n equals 1 is smaller than n equals 2, which is smaller than n equals 3, and that they're lower in energy, right? N equals 1 would be the lowest energy, then 2, then 3, then 4, and so on and so forth. Partially because we know things like the orbital is bigger, the electron spends more time away from the nucleus, so it's going to have more energy because it's less tightly bound. So, that's our first number. The second number would be the L value, this angular momentum. And it can be anything from 0 to 4, okay? Those are the values associated with it. And what we do is we associate it with what orbital. So a 0 would be an S, a 1 would be a P, a 2 would be a D, a 3 would be an F, and we're not really going to experience this, but technically 4 would be a G. The value of L tells us which shape we have. So if I have an N equals 1, L equals 0, that would tell me I'm in the 1s. Hopefully you also understand that if N equaled 1, L could not equal 1. There's no 1p. So we can't, there are some limitations. It's not like you can have any combination of these quantum numbers. They have to make sense. So next would be the M sub L. And this has a value of anywhere between L and minus L. And that includes 0. So what do I mean by that? If we had N equal 2, L equal 1, that would be the p orbital. And the m sub l would be anywhere between 1 and -1. So it'd be 1, 0, and -1. And that would correspond, that's three values for the m sub l, which would correspond to px, py, and pz. So here's kind of a breakdown as you're going through these different designations of what they will look like. I have a really great video posted in the resources section that goes through quantum numbers, as well as a really helpful worksheet that goes through the quantum numbers as well. I would really encourage you to go and check that out. This is the end of our second video for the chapter 7 slides.